All right, we're now going to look at some simple problems to solidify what we know on space and time. Problem 1 goes, an astronaut measures how long it takes for him to read a book to be 2 hours. If he's traveling at 0.8 c, how much time will it take for him to read the same book on Earth? What does this mean? The astronaut moving at 0.8 c is moving at a relativistic speed, meaning that the time he measures is going to be slower than the normal time stationary people will observe. The faster you go, the slower time passes for you. So another way to phrase this question would be to ask, what is the actual time it will take for him to read the book? Or what is the original time it is taking? What's the original time taken to read the book? So we're going to look at some few things. What we're looking for is t or delta t. Okay, and remember we got delta t is equal to t naught as the original time all over the square root of 1 minus v squared over c squared. Let's point out what we're looking for. We know that delta t is the dilated time that we're looking for, which is going to be longer than what we have here is 2 hours. T naught is our original time, which is 2 hours. C is the speed of light and V is the velocity of the object we're measuring. So let's substitute values in. T naught is 2 hours, so there's no need to convert this in and out of seconds because T and T naught will be in the same dimension, so you can leave it as 2 hours and you get an answer in hours. So delta T is going to be 2 over the square root of 1 minus. So you ask yourself, what's the velocity of a spaceship? We're told is 0.8 c. So squaring that is going to be 0.8 squared times c squared all over c squared. So it can get tempting to actually to multiply 3 times 10 to the power 8 times 0.8 and square that whole value. Well, if you look at it from here, you see that c squared cancels out. And then you kind of get a cleaner, nicer looking expression. So we end up with 2 upper roots 1 minus 0.8 squared. So let's solve that as 2 over the square root of 1 minus 0.64 2 over the square root of 0.36. And if you plug that into our calculator, you're going to have delta t as our new dilated time is going to be 3.33 hours. Okay, so this astronaut is moving at a relativistic speed, so time slows down for him, and external observers will measure a longer time for what he deems as slower. So let's move to the next question. This one is on length contraction. A spaceship passing the Earth at v is 0.9 c has a length of 100 meters. How long would the spaceship appear to someone on Earth? Remember our formula for length contraction. L is equal to L naught, our original length, times the square root of 1 minus v squared over c squared. You should be able to try this yourself now. L naught is 100 meters times 1 minus 0.9 squared c squared over c squared. C squared cancels out, so we have 100 minus 100 times the square root of 1 minus 0.9 squared. So that's 100 roots. Hundred roots 0.19. So that means L, our new length, is going to be about 43.59 meters. Okay, So that wraps it up for space and time.